So I finished grading your exams, but I got some stuff to take care of before I can give them back to you guys. But, so don't worry, I'll get them back to you guys soon. There's that. Anyway, where we're moving next is we finished our eliminations, right? We talked about E1 and we talked about E2. Now we need to talk about the next two there, the SN1 and the SN2, and what I did in the recorded lecture there was talk to you guys about SN2 and the basics of that, right? And the big important thing, or one of the important distinctions that we have between E2 and SN2s is the presence of a strong base versus the presence of a good nucleophile, right? And that's going to be extremely important, right? You guys have to know what a nucleophile is, and you have to know what a base is, and the properties of them, and how to determine which one, right, is going to, or how a molecule is going to be behaving in a specific instance, I should say. Okay? Now, when we talk about SN2, you'll notice that there's a lot of similarities to things like E2, right? And that should make sense. Right? Otherwise, they wouldn't have such similar names, right? The 2 represents that it's bimolecular. You see that these are concerted reactions. They all happen in one step, right? And you'll also see that much like our E2s, we have to pay very close attention to the stereochemistry of the product that's formed. Right? Remember, with an E2, we have to go back and draw our Newman projections and rotate so that we have the hydrogen in the right place. And then we can grab that hydrogen, and then we can see whether we make the E or the Z conformer, or excuse me, the E or the Z diastereomer of the double bond, right? And we talked about eliminations on cyclohexane rings, and how we have to have hydrogens in the right places there, and it was a miserable time for everybody. Except for me, I liked it. It was good, right? You guys are like, there you go. How much does an English major make again? Right? But remember, so we have to pay close attention to our stereochemistry with an E2, and the same thing with an SN2, right? SN2s invert the stereochemistry. If something started out, if our leaving group started out dashed, our incoming group's going to come in wedged, is what it is, and that's going to be important. And I'm going to catch you guys on that on the exam. Just like I caught you guys on the exam with the whole racemic mixtures. You guys remember what a racemic mixture is? Do you remember me telling you guys in class that I was going to catch you guys on the exam with that? Yeah. And I did. The prophecy comes true. I'm saved from another day of getting stoned. Okay? Not that kind. The biblical kind. All right. So, the same thing's going to be here. You guys have to pay attention to stereochemistry. I know you guys don't like it. Geez, Dr. H, it takes like 2.5 calories to draw a dash. It only takes 1 calorie to draw a straight line, right? Okay, then do it, right? But understand that the stereochemistry is important, and if you don't specify the stereochemistry, then you're not really answering it properly, all right? So if we do an SN2 reaction and we're at a chiral center, make sure you guys are paying attention to it, okay? It happens in our 2s. SN2 and E2s have to pay attention to stereochemistry. Got it? Why do we not have to care about it with an E1, or as we'll find out, with an SN1? Because both, and what's the intermediate for an E1? A carbocation. What do we know about carbocations? They're planar, right? I just end up scrambling things. That's how we get to this racemic mixture that I just talked to you guys about, right? So the same idea is going to come in with our SN1s, okay? But our E2s are nice. One step, you hit the carbon that is bound to the leaving group. Okay, you hit the carbon bound to the leaving group. Not the leaving group, the carbon bound to it. Got it? The other important thing we talked about is that when our leaving group is at a tertiary position, you are not going to do SN2. You're not. Ever, ever, ever. Asterisk. Right? For this class, we will not be doing an SN2 at a tertiary position. I've always made a promise to you guys. I'm not going to trick you guys. It doesn't mean the questions aren't tricky. Okay? But they're all based off of the same principles. You just have to understand what those principles are. And one important principle is recognizing what flavor of leaving group you have. Primary, secondary, or tertiary. That's a huge distinction that's going to help us pick which reaction is going to be favored. Okay? Because that's what we're building up to with this. I'm going to throw a reaction set at you guys and say, tell me the major product and tell me what the mechanism is. Tell me the minor products and tell me what the mechanisms are. Okay? And then you might even have to, give a relative estimate of how much of a preference there is. This is going to get formed 99% of the time, right? And your minor products only get formed 1% of the time, that kind of thing. All right? So be careful and just understand that that's what we're building towards, okay? So, tertiary leaving group with a good nucleophile but a weak base. So we will do a different reaction in this case probably, right? But we'll get to that in just a second. All right. Not what I wanted. There it is. So, so show me what the product's going to be here. Remember, I might ask you guys tricky questions. First thing we need to do whenever we're presented with a problem like this, start to gather evidence, okay? Start to use the eyeballs. So what do we have? Now we'll start with our substrate there, the alkyl halide. Do we have a good leaving group? Yeah, we got a really good leaving group. Okay? What flavor of leaving group is it? Secondary. Okay? So we got a good leaving group. That doesn't exclude anything yet. Okay? Because all of our mechanisms are going to need good leaving groups. Okay? We only have a single leaving group to deal with, so we can't make an argument about one reacting faster than the other. We'll do a couple examples of that later. Okay. We have a secondary leaving group that puts almost every reaction still in play. Can I do an E2 on a secondary leaving group? Yes. Can I do an E1 on a secondary leaving group? Well, yeah, I could. Wouldn't be great, but we could. Can I do an SN2 on a secondary? Yeah. Okay, so all three of the mechanisms we know are still in play, right? So if all three of them are still in play, which ones are going to happen? Are they all three going to act equally, though? No. No, that's the distinction, right? Can all three of them happen? Yes. Will they all three react to a 33%, 33%, and 33% of the time? No. You guys with me on this one? It's very important. I can just see the understanding oozing. Are you guys with me on this? All we're doing is building evidence and saying, can we eliminate any of our mechanisms so far? All three of our mechanisms are still in play, but, right, some are going to be better than others. Okay? And we'll talk a little bit more about that as we go through. Okay, so we've kind of beaten to death the alkyl halide there for what we can do so far. We take a look at what else we have with it. I've got an O with a minus charge. What is that? A what? How do you guys know it's a strong base? We have a localized negative charge. How do strong bases want to act? Like a base. Okay? They want to act like a base. What do bases do? They grab hydrogens. Which of our mechanisms involve grabbing hydrogens? Our E's, right? And with strong bases, we prefer our which mechanism? E2s. You guys with me on this? We have a strong base. It's a secondary leaving group. It's going to prefer to eliminate. Okay, so here's a new problem that looks identical to the old one, even in the color, and even where I wrote it on the screen. Okay, I know I'm being dumb. I got a point that I'm going to make with this. Okay? We got a secondary leaving group. We have an O with a negative charge. What do we know about O's with minus charges? They are also good what? They are good nucleophiles. Darn it, right? What makes a nucleophile good? That's how they behave, right? Yeah, you're correct. But what makes something want to go after something positive?
It can handle the charge.
What charge?
The negative charge.
So what makes a good nucleophile?
It has like a negative charge.
Right? It's feeling negative. What does it mean to be a nucleophile? Well, nucleus is positive, right? And phile is to like something, so it likes positives. It wants to go after something positive. And if you want to go after something positive, you yourself are feeling negative. Are strong bases good nucleophiles? Yes. You see the distinction though. A base is going to go after a positive feeling hydrogen. A nucleophile just goes after anything that's positive. It's got loose morals, okay? Anything that's positive, it's going to go after. What's more important to recognize though in terms of picking reactions and what mechanisms? Acid-base reactions are very fast reactions, kinetically, okay? And they tend to be favored thermodynamically most of the time too. And if you're favored kinetically and you're favored thermodynamically, what does that mean? You're going to happen, and you're probably going to happen first. Why is that important? Why am I bothering to tell you guys this? Because if you have the choice of something acting as a good base or something acting as a good nucleophile, what's going to happen more frequently? It acting like a good base, okay? Can this still act like a good nucleophile though? Yes, it can, okay? And that's where we live in the gray, okay? I know you guys want black and white, the up and the down, okay? It doesn't work that way. We gotta live a little bit in the gray. it's going to favor one mechanism over the other, and therefore we can predict a major organic product. But multiple mechanisms will happen. Okay? So, in this case where we have a strong base, okay, a good leaving group that's secondary, okay, we can have both of these products form. Good. So why don't you guys go through and draw the mechanism for both of these and give me the name of that mechanism. This is the coal elimination, followed by the Freddy substitution. And not that kind of name, right? What mechanism is it? E1, E2, SN minus, and 2, that kind of stuff. Isn't that a pleasant thought, though? If you guys become chemists, you could come up with your own mechanism and torture generations of students after you. The hillside rearrangement and tears just start falling. I'll get there someday. Yep. Mm-hmm. Oh, hang on to that thought. Right? The answer is it can. But in what mechanisms would it work? Right? No, right? Don't do an E2 like that. E2s happen in one step. There's no carbocation. Right? Yeah. All the 2's have one step. The 2 tells you that it's bimolecular, but that doesn't mean there's 2 steps. It means there's one step and 2 things are involved with it. Right? Okay. Which mechanism is this? Mm-hmm. Okay. Using the book. Now. So what's this going to do? How is my negative thing acting? My negative thing is attacking what? A hydrogen. So it is acting like a base. Strong bases are used in elimination, specifically E2s. You guys with me on this? Remember, elimination, we're looking for a hydrogen next door, right? At the alpha position to the carbon that's attached to the leading group there. Okay? All right, so that would lead to my elimination product here. How is my negative thing acting here?
Like a nucleophile.
Like a nucleophile. How? How so?
It's attaching what would be a carbocation, but it's not.
What do you mean by would be a carbocation?
So when the iodine leaves, there's like a gap there, like a positive.
This all happens at once. Right? That's one of the definitions. This is important though, right? This all happens in one step. That negative comes in as that iodine is leaving. Yeah.
Does it act as a better nucleophile than iodine?
Huh?
Does it act as a better nucleophile than iodine?
No, it doesn't. That's going to be important also. We're going to learn about the dorkiest sounding reaction in just a little bit. I mean, it is just, you guys will see what I mean in just a little bit, but that's an interesting thought, right?
The carbon is partially positive because of polarizability.
Because it's attached to electronegative leaving group, right? Okay. No carbocation. It's extremely important to recognize that. Because if you have a carbocation, you bring in all kinds of trouble. Rearrangements and shifts and all this other kind of stuff can happen. You are not going to see that if you're doing an SN2 because no carbocation forms. Okay? This all happens at once. That negative comes in as the leaving group is leaving. Okay? That negative comes in as the leaving group is leaving. So my product here, right, is going to be, right, this guy. What else? What other mechanisms can we have happen here? Ooh. Now, we got a secondary leaving group. We've already dealt with the strong base, right? We've already dealt with the good nucleophile. Is there anything else in our reaction?
Can you do that SN1?
We might be able to, right? We haven't talked about it yet, right? But what other mechanism have we talked about? E1. What's an E1? It's an elimination that's characterized by what? A unimolecular rate determining step, yes? Yes, it is. Right? What does that mean, though? Ignore the whole unimolecular thing. If I'm telling you that something's unimolecular in the rate determining step, what does that really translate to you guys in your brain?
2 separate steps.
Maybe 2 steps.
Just one molecule?
There's one molecule involved. It's really hard to make it because it's the rate determining step. What's an annoying molecule? Huh?
Carbocation.
Or carbocation, right? Your E1 and your SN1 are going to be characterized by carbocations. Okay? And if you generate a carbocation, what happens? Your will to live slowly fades each time. Right? Because we have to deal with rearrangements and shifts and, okay, it makes a racemic mixture and it does all this, right? So when you're dealing with your E1s and your SN1s, you're going to be forming a carbocation. How do I want to put this? What characteristics help in the formation of a carbocation? What characteristics help in the formation of a carbocation? AKA, what carbocations are easier to make? Tertiaries would be easier, right? Can we make a secondary? Yeah, right? We could. Does a molecule really want to? Probably not, right? It's hard to make a carbocation, but could it make could we generate a carbocation here? Sure, right? But it wouldn't be easy, but it could. So, why don't you guys see if you can take this and do an E1 with it? right? Leaving group leaves. A base is going to come along and grab the hydrogen next door. More likely it's going to be this guy, given the situation, right? But remember, with an E1, we could also use that guy there, right? A weak base, a stupidly weak base. I'm insulting ethanol. Stupid weak base. Right, so we'd end up as that. Right? What does that look like?
How is that any different than the?
Indeed. How is that any different than my E2? The answer is, it isn't. Right? I didn't say that the different mechanisms are going to make different products, right? They could in some cases. They could in some cases, but in some cases they're going to end up with the same thing. Right? Good. All right, so then the question, we still haven't quite finished yet, because which one of these is going to be preferred? Secondary leaving group, strong base, okay? We're going to be favoring our eliminations, okay? Acid-base chemistry is going to usually happen faster than our nucleophile chemistry, right? If you want to think about it in that way. It's going to want to grab that hydrogen and do an elimination before it can do the substitution. But there's not a huge preference in this case. It might be something like 60-40 or 70-30, something like that. So we'll kind of split the difference and say maybe 65% and 35% here, something like that. Is there still a preference though? Yes. Is it a huge preference? No. Good? Complete understanding?
So we could just come up with numbers.
I can. But what I would ask you is what's the major and the minor products, right? That's what it is.
Which one did we say that it preferred?
Even calories. Mhm. Which indeed, right? Whenever you're left with a question like that, how do you think you should approach it? Yeah? In this one, you can assume that it's there. Right? If I didn't specify the stereochemistry, right? But there's two hydrogens next door to it. So there's always gonna be one there, right? Yeah. When you have to be careful is when it's next door to something where there's only one hydrogen. Right? Then you have to start to look at, the correct orientation, all that stuff. Okay, so we have a good leaving group, right? What flavor of leaving group is it? Tertiary. That automatically eliminates a mechanism. Which one? SN2, so we cannot do an SN2 here. So we're only left with E1 or E2. Maybe SN1, right? We'll get to that in just a bit. We're already down to only 3 mechanisms. All right. So if we're thinking elimination, what do we have to do next? We have to have a good base. Do we have a good base? How do we know it's a good base? Localized negative charge, right? Okay. If we're going to do an elimination, what else do we need to have? We do have a good leaving group, yep. What else do we need to have? We have to have hydrogens next door to our leaving group, right? To do our elimination. Do we have hydrogens next door? Yes. How many next doors do we have? Ooh, how many? Crud. So which one is going to be next door? How many possible hydrogens are there? So which ones of those are going to react? Yeah. Which ones of those are going to be 180 degrees? You guys get the point I'm asking? The point is this. So when you have a leaving group, okay? When you guys have a leaving group like that, if you have 2 of your hydrogens next door on the ring, one of them is always going to be in the axial position to that leaving group. If you take a look back at the example that we had, right? If you take a look back at the example that we had previously, right? There we only had 1 hydrogen next door. And then we really have to pay attention. If I've got 2 hydrogens next door on the ring, one of those is always going to be in the right place. Because one's always going to be axial. That means, we can always line something up properly. Makes life a little bit easier, right? Good. But the point being what? How many next doors do we have? We have this one, right? Is that next door? Is that next door? Is that next door? So where's my elimination going to happen? From all of them. So which ones do you guys need to do? All of them. And then do what? Right? Is one of these better than the other? What was it, Sesame Street? I had that song like, which one of these is that? Was that it? You guys don't know what I'm talking about? You guys are getting young. I'm getting older. You can come up with new these songs for you. Well, then I can just claim I made up the songs. And you guys have to listen to me yammer on about songs, right? But if you're left with an option, hey, we've got 3 next door neighbors, you do all 3 of them and say, well, geez, one of these has to be better than the other ones, right? This guy out of the way for now. Ooh, that's not it. Oops, I'm dum-dum. Good. Those are 3 possibilities. We'll come back and do the mechanism in a second, right? So those are the 3 possibilities? Yeah. Okay, which one of those is better? Right? What's the only criteria we really learned for distinguishing between alkenes that are formed? Sort of. What's a happier alkene? What makes an alkene happier? The more stuff it has around it, right? Tetrasubstituted versus tri versus di, right? Okay, well, what's the substitution of these? They're all pretty much the same, right? Crap. So which one of these forms? All of them. Probably. As far as what we'll talk about in this class, right? There's probably going to be a slight preference for the, I would probably say the, well, geez, never mind, I was about to say something dumb since I'm being recorded. I don't want to be thought of as a fool. I'm just going to do dumb dances for you guys and record those instead. Right? But there's probably is going to be a preference for one of these slight, right? We don't really care about that. What I do care about is that you guys understand that all 3 of those will form. And that for our purposes, all 3 of those will form to the same degree because there is no distinguishing characteristic between them. Okay? You guys get what I mean with that? They're all tri-substituted alkenes. They're all of equal stability. So if we just wanted to finish our journey, right, we could draw our mechanism. Right? You guys could fill in the blank for the red and the black one too, right? Can you guys draw the E1 for this? I just feel like my stomach's gonna sing you guys songs. Oh, I didn't really have breakfast. Right? Remember for E1, generate your leaving group. I mean, not generate your leaving group. Make your leaving group leave to generate your carbocation. And then you come in and do the elimination, right? So how will the products look different for my E1 than my E2 in this case?
No change.
Hmm?
No change.
No change, right? They'll be the same. Will the mechanism be different? Sure. Would we be able to tell just by looking at the final product? No, right? Is that always going to be the case? Are E1s always going to look like E2s? No, right? Why? What very key important difference? The formation of the carbocation could lead to rearrangements and all this kind of stuff, right? Don't get complacent with your carbocations. Okay? That's going to be what you guys miss on the next exam. Oh, I got a carbocation, and you guys go on. Right? Don't. Always stop. Look to see if you can rearrange, adjust, change, whatever you guys need to. Okay?
Dr. H, I have a question.
Yeah.
If you scroll to like the last reaction we did when we did the E1,
Yeah.
no carbocation formed there.
This?
Oh,
Yeah.
okay.
Freddie, you think I would make a mistake like that? This is amateur hour. Come on. What am I, a biology major? Just kidding. See all the down votes coming on that. No. Always got to have a carbocation form. Okay? Rate determining step. It's hard to form carbocations. That's the point I want to keep impressing on you guys, though. Okay? It looks easy to us because, oh yeah, just draw an arrow, thing pops off. It's deceptively easy, right? We have to break a sigma bond. That's not easy to do. Okay? So it's not that quick for that to happen. It can happen, but it's pretty darn slow. Okay? All right. There it is. I missed the opera. Wasn't that last week where we got serenaded in this class by the So what do we got here in this reaction? Got a good leaving group. Leaving group is good. Okay. Got a strong base. Strong base is a strong base. Got a good nucleophile, right? But what flavor leaving group do we have? Primary. Now, what is this going to tell us? A primary leaving group, okay? A primary leaving group is going to tell us that either an E1 or an SN1 won't be happening. It won't be happening. Why? Because we would have to generate a primary carbocation along the way. And for our purposes, a primary carbocation just is not going to happen. Okay? We're going to learn maybe 2 mechanisms in total where a primary could form. But for our purposes here, they're just not going to form. Okay? Way too high an energy situation. Way too big a hill to climb to form a primary carbocation. You would need some pretty high temperatures to form a primary carbocation. But if you're at high temperatures, you start to favor eliminations anyway. Okay? So you would probably get a more preference for the eliminations even at higher temperatures. Your E2s, I should say. So primary is important to recognize. We won't be doing an SN1 or an E1, which leaves us with SN2 and E2. Okay, do we have a strong base? Yes. So is an E2 in play? Yes. Okay. With a primary and a good nucleophile, you're pretty much always going to favor an SN2 though. Okay? It's a similar situation to what we dealt with at the beginning where we had the secondary there. Is there going to be a huge disparity between the two? No. But an SN2 is going to be favored with a primary leaving group and a strong base. Okay? So our product here I'll put some colors in here just to make life easier for you guys. Okay. Good? Careful when you're doing these. What tends to happen is you guys go on a diet. It's not the good kind of diet. I call this the carbon diet. The carbon diet is where you guys just randomly cut out carbons from your life. Alright? What happens when you cut out carbons from your life? You miss points on exams. Not a good diet, is it? So, joking aside, what do I mean? If I started out with 4 carbons here, okay? If I started out with 4 carbons here, make sure that I have my 4 carbons there. Got it? Very often what I see happen is this. You guys just cut out one of those carbons. You're like, yeah, screw it. 3 is close enough to 4. Okay? Be careful with your carbons. I know why you guys do this, right? Our arrows show like the oxygen is taking the place of that carbon. No. It's making a bond to that carbon, right? It's not taking the place of that carbon, it's making a bond to that carbon. So just be careful of that. Okay, so there's that. What would the E2 look like? Oops. Hydrogen next door. Right. Good. Why might an E2 not be favored? Well, we're not making a great alkene. Okay. I've got one of these terminal alkenes, that's not all that great. But we won't be doing an E1 or an SN1 at all. Okay, so now our choice is just SN2 or E2, and SN2 is going to win. Good? But we got to think. I know. It's a lot on Wednesday. Let's say that I wanted to do an E2 reaction here. All right, so I bring in some kind of nucleophile. And I want to do an SN2 reaction with these 3 molecules. Now we got to stop and go what? Well, these are clearly not the same, right? But what is the same? What is constant in all 3 of these molecules? We have a good leaving group, and that leaving group happens to be what? Primary. So we might expect that these would all react and at the same rate and all this kind of stuff, but that's not the case. Okay? The one on the left is going to react far more quickly than the one on the right. Now, why would that be? So what limits a SN2 reaction is what I'm really asking. Because if I ask you this, does an SN2 reaction happen at a tertiary position? You guys would say? No. Why? Well, Dr. H, you said so. You are wearing a nice shirt and you look trustworthy. And that's my reason. Right? What happens with an SN2 reaction? When we're drawing an arrow with an SN2 reaction, what are we representing? We're representing that our incoming nucleophile is attacking on the opposite face of where the leaving group is leaving. Okay? It's coming in from the opposite side of the leaving group. Got it? Now, this illustration always worked better when I was in the bigger classrooms, where I had like 300 of you guys. Right? Here, you know, okay, I've got, what do we got today? Wow, we got all 12 of you guys today. Right? The limiting part of an SN2 reaction is something that's known as sterics. Okay? Sterics is basically when you got too much stuff around. Sterics is when you guys are walking through the woods and you find a trail, you walk on the trail. Right? Could you walk through the woods? Sure, but there's a bunch of stuff in the way, right? It's going to take you longer to walk on the uncut trail than it would on the defined trail, right? That's what sterics is. Sterics is stuff in the way. There's stuff around. So let's think about it like this. So here I have a carbon. Okay? Here I have a carbon. Here it's bound to my leaving group. Okay? If I have the simplest of situations, where I just have this, a methyl halide. We could call it methyl bromide, methyl chloride, methyl iodide. Okay? If we do an SN2 reaction, what is blocking the opposite face, right? So remember, what we're going to be doing here is we're going to be having some nucleophile coming from here, while that leaves there, right? So what does that nucleophile have to push through to get to that carbon? Well, it has to push through what? Some hydrogens, right? Is hydrogen all that big and bulky? No. Does it have bulk? Sure. Are you with me on this? If I bang my elbow, perfect. Let's make this a little bit more complex. For emphasis sake, right? Now I've got a primary leaving group, right? Our leaving group is bound to a carbon that's bound to one other carbon. You guys starting to see the point already? Is there more junk around this carbon? Yeah, right? You've got the hydrogens here, right? And the hydrogens here. Can the nucleophile still get in there? Sure, right? Sure. Ah, crap. All right. Don't worry, give me a minute to paint my cupola here. You guys really want me to draw the other one? You guys get the point? You guys get the point? As soon as I put more junk around this, we're just going to be slowing down that reaction based off of sterics. Okay? Because literally what has to happen is the nucleophile has to come in here and push all these other things out of the way. Okay? It's got to push all this other crap out of the way, and then it can hit that carbon. You guys with me on this? So the more stuff, the more sterics, the more junk that you have close to the carbon that is bound to the leaving group, the more you're going to slow down an SN2. That's why a tertiary carbon is not going to undergo an SN2. There's too much stuff to push out of the way. Okay? But we also have to look on the next door carbon, like we do here, right? Our next door carbon has a bunch of junk on it also. And that's going to start to slow things down. Can this still do an SN2? Yeah, but it's going to be really slow, right? We've got that huge T-butyl group next door to that, okay? It's really going to slow down that SN2 reaction. But can an SN2 reaction still happen? Yes, but what happens when you slow a reaction down? What does that mean? The slower reaction, it becomes a minor product, right? It becomes a minor product. The faster reaction is going to react faster, and if it reacts faster, it's going to react more, and if it reacts more, it becomes a major product. So very rarely can we completely shut down mechanisms. They just become prohibitively slow, might be the better way of saying it. But that takes too long to say, so I just say it doesn't happen, right? Good? So take a look for sterics. So what I'm starting to build for you guys here, what I'm hoping to build for you guys is all these different selection criteria. If we're dealing with an E1 or an SN1, you're not going to form those because you make a primary carbocation. That's not going to happen. SN2 is not going to happen at a tertiary position because of sterics. Well, we would say steric hindrance. Okay? It just hinders the nucleophile from coming in. It's got too much junk in the way. Okay? So we slow down these reactions, and therefore they do not happen as frequently. Got it? Good. Cool. Tomorrow we'll be in lab, but we'll just be kind of wrapping some things up. We'll do our NMRs and our IRs and that kind of stuff. Okay? And then we'll be done with the first 3 labs, and then we'll start the next one next week is what it is. Sound good? So we don't need to prep anything for next week, for tomorrow, I should say. Just make sure you guys do bring your goggles and that kind of stuff too. All right? Cool. I will see you there then.